today. I am, this, as you know, summer is hard for all of us. And I wake up in the morning not knowing what day it is. Sometimes I don't know what day it is, even when I get here. A little bit of good news for you. There were a couple ambiguous questions on the last midterm, so we're tossing a couple out. So everybody's average is going to go up a couple points, so that's nice. And like I said, you guys are, I know there's a feeling the exam is hard and you're not performing as well. And I will tell you, the midterm too, that was one of the hardest exams I think I've ever written. I wanted to challenge you guys, and actually you did it. You rose to the challenge very well. I was impressed. But that will be the hardest one you see. It'll be easier from now on. And one other thing, some of you must have recognized fully half of it was right from the homework with no changes at all. So I hope you see a lot of them. But we did find out there are so many questions in some of the homeworks that even if you do them, like 15 times, you don't see them all. So we're going to try and lower those, the numbers. So if you there's no way that you should have to do it 15 times to see them all. I'd like to see, that more like, 6 to 8 times through you get to see them. You don't have time to do every homework 25 or 30 times to see all the questions. So we're working on that. So update on that. Hopefully this week we'll get to it. So we have been talking about electrons that have more than one electron, atoms that have more than one electron, so multiple electron systems. And our idea is very simple. It's just we'll take the standing waves, the hydrogen atoms, so one proton, one electron, those standing waves, and we'll just use them over and over again for as we add electrons, go across the periodic table, add one proton to the nucleus, one more electron, one proton to the nucleus, one more electron. And let me zip through here to about where we stopped. We'll go here and just review here. And we found there were several rules. One rule is we try to fill lowest energy to highest energy. Every electron must have a unique set of quantum numbers. So if you give a set of quantum numbers that the first 3 define a standing wave, one of the orbitals, and the last one, whether an electron has a magnetic spin up or spin down, and each electron having a unique set of quantum numbers, actually that infers part of this thing. We said when we first started that atoms are mostly empty space. So we have empty space and the nucleus is in the center. The electron cloud is huge. If the nucleus was the size of a pea, then the electron cloud would be the size of a football stadium. So it's mostly empty space. The electrons are flying around in there. But one of the reasons matter feels solid, why matter has mass to it, resistance to it, is the fact that these electrons can't occupy the same space at the same time, if you'd like. There is this overlap in space. Pauli Exclusion principle says the electrons have to spread themselves out. So we applied that rule, and so 2 rules so far: start from the lowest energy and build up. Make sure you have all unique sets of quantum numbers, and there's the rule for M sub s that says parallel spins are better than anti-parallel spins. And if you have degenerate orbitals of the same energy, then the electrons go in spin parallel first. And the electrons interact with each other. This is one reason they go in spin parallel. Spin anti-parallel, this tiny little anti-magnetic interaction is a little higher energy than all the spins parallel. And you even know that from a macroscopic magnet. They'd rather be aligned together, and you have to put in energy to flip them opposite. So this was called Hund's rule. We don't care if we know the names of these things, but degenerate orbitals have parallel spins. And that allowed us to write what we're going to call electronic configurations. And we can go through this quickly because we saw it last time. But we kept track of the full magnetism. So something is paramagnetic. I don't think that word appears here. So we'll just write para in front of here. Paramagnetism is this property of at least one unpaired electron. When the electrons are all paired, there is no magnetism, and it's real magnetism. It's the electrons or the compound being attracted to a magnetic field. And we'll see it happen. We'll wait till we have a molecule where we understand it in a molecule, but we'll attract some molecules that have this property to magnetic fields. But as we said, once the electrons are all paired, you have no magnetism, and you just continue to fill up the orbitals. Now, the 2s orbital is higher in energy. It has a greater n, but I've written them all on a line just to fit them all in on this chart. But you continue to fill, and the rules say 2p, these are the p, they're slightly higher energy than the 2s. We're going to find a reason for that. It's principal quantum level 2, but there is a little energy difference between those, and we'll find out why that is today. So the fifth electron that goes in the 2p rather than the fourth. And then we would just continue, and you can see as you go carbon, 2 unpaired electrons. Now I'm using Hund's rule. I'm going in spin parallel. And I can keep doing that. Here's nitrogen and 3 unpaired electrons. So very strongly paramagnetic is nitrogen atoms. There's oxygen now, less paramagnetic. We're going to fill that in. And we can see px, py, pz. We'll start to drop that notation and just put 2p5. This is all the p's. We have to remember it's L equal 1, so there's 3 equal degenerate orbitals, 1 for each value of m sub L. Oh, that was from last time. We didn't do this, did we? I'll talk through this. We'll talk through this one because I don't remember if we did it or not. When an electron spin flips, which of the following is not altered in energy? So if I could have the output of the yeah, you did it. So an electron spin flips, which is not altered in energy, and we know that everything else being equal, if there's nothing around, for instance, the hydrogen atom, which is 1 electron, it can be spin up or spin down, and we don't even know which one it is. And there's only kind of a preferred orientation if there's other electrons around that it's trying to align with. So if you're going to flip a spin in hydrogen, that is an extremely low energy interaction. But if you do it in helium, where there's a pairing interaction, it would be very resistant to going the same spin in, or flipping it over the same spin in the same orbital. So let's look at what this is. So here they are, nitrogen, oxygen, and fluorine, the electron configurations for all of those. And we can see for fluorine, there's one of those cases where it's just one unpaired electrons. That one could have been spin up or spin down. It doesn't matter. Those are equal energy states. These two, if you flip a spin over, it would have an anti-Hund's rule situation. And they would work their way back to in phase, all spin up. We can actually watch that happening. I was trying to get the demo in person, but I couldn't get my act together. But you can visualize this in a couple ways. If you put a bunch of metronomes on a system like this, this is a table resting on soda cans. So that means that as a metronome goes, it will slightly move that table because it can roll back and forth, only very, 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 very slightly. But that means that the electrons, I'm going to call them metronomes, are a coupled system. They can sense that the other one is there because they can sense that there's a metronome swinging next to it, and they're all trying to move the table. So there's this coupled system, this interaction energy. And watch what happens when you start the metronomes ticking just randomly. So if they were just on a bench top, fixed, and they couldn't interact with the table, they would stay like that, out of phase. But look what's happening. You can see just a little wiggling of the table. And that wiggling of the table is enough. Check that out. That they all precess into phase with each other. And this must look like, remember, let's pause that. Oh, let me go a little farther so it's, oh, cool. Wow, good pause. So this looks like something like the d orbitals. So for d orbitals, L equals 2, so there's several values of m sub L, -2, -1, 0, 1, and 2. And so there are 5 degenerate d orbitals, and if you had to fill them with electrons, you would fill them one at a time with Hund's rule, all with the same spin. And you might say to yourself, well, the electron, if you're just adding another electron, how do you know if it goes in spin up or spin down? Well, it could go up either way, spin up or spin down. But if it sits there long enough with the other electrons, the lowest energy state, because they interact with each other, will be all of them spin up, same spin. Okay? So that's a kind of an analogy of interaction in a weakly coupled system, all those electrons lining up with each other. That is just really cool. I will try to do that in person again because it's kind of just fun. Okay, that last one could be up or down, so we have this. So this one you guys can do. So let's do this. Talk about this amongst yourselves. Which species in its ground state, and remember its ground state is the lowest possible energy state, so we're filling the lowest values of n first, along with all our other rules, which exhibits a absorption from n equal 1 to n equal 2. So here's a ground state to this first excited state. Talk about that, and we'll take a vote. Okay, let's turn on the voting system. It's on. And as you know, guys, I hope you're logged into the EduRoam site, but go ahead and start voting there. And I hope you're responding on EduRoam. Okay, it looks like many of us are thinking fluorine, and I agree with the fluorines. So what am I going to say here? Here are the electron configurations. Fluorine can do a transition where we have the n equal 1. Oops. There's n equal 1. For these, n equals 2. This is the s, p, p, p orbitals. So for fluorine, there's room to go from the 1s to the 2p, that transition. For the other two, there are no open orbitals. There's no open wave function. There's no standing wave that this electron can adopt with principal quantum level 2. So that's not possible. Only this fluorine has a available space. So same thing here. For which species does paramagnetism increase upon ionization? Now we have to ionize. So that first one, we were specifying that I was going to go from principal quantum level 1 to 2. So n equal 1, n equal 2. That is a fixed amount of energy that we could calculate. Now I'm going to ionize it. So I'm going to remove the electron from the proton, or protons. And that ionization energy is where I go from the highest filled state, so the electron that's in the highest energy, and remove it completely. And we know that requires energy. And when I get to the ionized state, what's the energy level for the ionized state? How much energy does that one have? 0. That's the 0 energy state. And again, 0 energy, we just define that to be 0. Relative, we're always talking about relative energies. So you don't have to think of, oh, that's the 0 in energy and it's the end of the universe. It's just they're spread out far enough that they don't have any interaction. And we do this thing that we say we can do with state functions, is arbitrarily set 0 where we want it. So we just set that configuration to be the 0 energy state. So I go from some negative energy state. We know all the energy levels are negative, up to 0. That's an absorption of energy, and just enough to kick it off the nucleus is what we're shooting for. So we'll talk through this one together since we've already talked enough about this. We're going to look and see, does paramagnetism increase when we do this? So we can look at all the configurations. Here they are. So neon, nitrogen, carbon. And we're going to remove an electron entirely now. So we're going to get a charged species. We're going to get the positive charged species. And we want the paramagnetism to increase, I think we said. So for carbon and nitrogen, if we remove an electron, ionize that, or ionize that, it still has paramagnetism, and it decreases. So these were paramagnetic to start with, and the paramagnetism goes down. They're less magnetic, fewer unpaired electrons. But we can see neon, if we ionize that, it goes from a diamagnetic, that means not paramagnetic, the opposite, diamagnetic species to a paramagnetic species. So that's the one that would increase in paramagnetism if we did the ionization experiment. Now, oh, here it is. If you're all logged in. Okay. Everybody happy with that? Fantastic. So now you see this one, and we'll talk about this one among ourselves, which species can have the electronic configuration. And now we're going to start to use some notation here. And we talked about this briefly last time. This, when I put helium in brackets or some other compound in brackets, means I'm talking about the configuration where it has everything sodium has or everything helium has plus these other. So it's just shorthand so you don't have to write out so many orbitals. So this is helium, so 1s2, 2s2, 2p5, 3s1, which can have that electron configuration. So talk about that among yourselves. And I think we have some help up there on the screen. Talk about that among yourselves and see what you think. Cal students? Yeah? Are you guys Cal students, regular Cal students? Are you sophomores, freshmen? You're going to be a sophomore? Going to be sophomores? So you're taking Chem 1 as a requirement? You're late.
Yeah.
You're late.
I was late.
You're late. Okay, let's see what you're thinking about that. We'll go back to the poll here. And, oops, that's the wrong poll. There's the poll. And, oh my goodness, I can't even really differentiate. A few extra maybe here is all, but A is also popular. So let's see what you're thinking. So here we have the electron configurations, and notice, so here's sodium, and we know sodium up there on the big screen has this electron configuration. This is sodium, the neutral atom. So there's one electron for every proton in the nucleus. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. And for sodium, Z is 11. Z is the charge on the nucleus. Z is the number of protons in the nucleus. It's the atomic number. So this thing is neutral. And it can have this ground state electron configuration. So it's the lowest energy state. We've determined that. Sodium, we have neon. Sodium has 11 electrons in its ground state. But if it's positively charged, that must mean it has one fewer electrons than the protons in the nucleus. So this is sodium ionized. So one of these electrons is missing. It's been ionized. So it can have this configuration. And you'd say, well, if I'm going to ionize it, wouldn't I ionize this electron, the highest energy electron? The answer is yes. But you could still have the ion in a slightly excited state. So 2 steps, ionize it, and then promote an electron from 2p to the 2 level to the 3 level. So this is excited state sodium. We'll do the little excited state symbol there, but it's sodium plus. Fluorine minus, same thing. Fluorine, if we go over the periodic table, has Z equal 9. But it's the negative ion. So that means I've added 1 electron. It has an extra electron. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 negative charges to 9 positive charges. We'd have an overall negative charge on that species. But same electron configuration. Okay? So either answer is okay. I think that's why we saw the spread there. But it brings up one of those important things. If you take nothing else home from Chem 1, take home the fact that it is only Z, only the number of the protons in the nucleus. The number of protons in the nucleus is the only thing that determines the identity of the element. It can have more neutrons, it can have more electrons. So this electron configuration is not sufficient to identify the atom, is it? And we can see brilliantly here, sodium plus and fluorine minus. If I didn't have those there, you could not tell what element that was. Okay? It's one of those fundamental things. And you know, if I say it a lot of times, it's a fundamental thing, and there'll be an exam question that makes you think about that fundamental thing. In fact, you should always think about the fundamental things. If you're stuck on a problem, if it's not obvious, you should probably write down all the fundamental things that I say when I say. If you take nothing else home from Chem 1, you should be writing that down, and you should apply those things. So if it's a electron configuration problem and you're stuck, apply the fundamental things. The fundamental thing is the charge on the nucleus, the number of protons in the nucleus, determines the element. There's other fundamental things you should apply. If you take nothing else home from Chem 1, a combustion gives you carbon dioxide and water. If you take nothing else home from Chem 1, breaking bonds always requires energy. You take nothing else home from Chem 1, Q, the reaction quotient, can be any number anytime. It is not related to K. It is not related to K. You can relate it to K if you want, but you can mix up a reaction any way you want, and that's the Q when you mix it up. Then if you want, sure, compare it to K and see where it'll go. But it can be any number. So apply those things. I think I should remember them. They're fundamental things. Entropy always increases for any process that happens spontaneously. And that means delta G is negative. And it could be the reaction delta G, the instantaneous one. So if there's no free energy difference between products and reactants, that reaction isn't going anywhere. Equilibrium, instantaneous. If there is a difference, if the products are higher in free energy, then it's not going there. That's delta G positive, instantaneous. The real-time situation, delta G reaction. Delta G standard state is just a state that we set up. Everything's 1 atmosphere or 1 molar concentration, and pure liquids and solids are just present in some amount. And that difference tells us same thing. Will it go? If delta G is positive, it's likely to go. It's spontaneous in the reverse direction. If delta G is negative, the products are down here, and I can go downhill. Delta G is positive, or excuse me, negative. The reaction will go towards products. From the standard state is all it says. You made it in the standard state, and you measured it's the same delta G. You made it in the standard state, and you measured the free energy difference between the two. So it'll tell you from standard state where it will go. And it'll tell you where it'll stop, because delta G standard also tells you what the equilibrium constant is. So in that special case, standard state free energy says where you'll go from standard state. Everybody's 1. Of course, you're not going to stay everybody 1. You'll go somewhere. You'll go to equilibrium, and you get all that information from the standard state free energy. I don't know why I went off on a tirade there, but I just did. Fundamental things. That's why we're talking about. Take home the fundamental things and apply them, especially if I say them over and over like that. Okay. Oh, nuts and bolts. We'll do that next time, or you'll do that in discussion. Maybe not get to a discussion this week, but next week. So here, we're going to do this one. Easiest thing to do might just be to start that one and then just go to the first slide this way. So we're going on to our next section, our next topic. We are still talking about the electronic states. Quantum mechanically, we're still just talking about atoms, so we have to get to molecules. Atomic properties, quantum atomic properties, and these are the things you should know. And again, this is something you can do if you're at the exam, you're preparing for your exam. Just read through these. Go back and say, do I know? Can I explain the hydrogen emission spectrum and identify the electronic transitions? Well, after 10 minutes here, we will have covered it. You can go watch the lecture section. You can do a homework. You can go to the reading for this lecture. So homework 27, lecture 27, will have reading and video and homework all about that. So we know the energy of transitions. We've done that. It's simple for hydrogen-like. It's exact. If you have 1 electron, Z can be anything, but if you have 1 electron, then this is the energy, exactly. Z squared over N squared, our little infinity is just a label for R. It doesn't mean anything in particular. It is the ionization energy. So it's when the electrons are equally separated in a 1 proton, 1 electron system. This is the ionization energy. How much it would take to remove an electron from one hydrogen atom. There it is in joules. Here it is in kilojoules per mole. You have a mole of electrons, a mole of hydrogens, and you're going to remove a mole of electrons. It takes 1,300 kilojoules per mole, really a tremendous amount of energy to remove those. You can break bonds for much less than this. Break a mole of bonds for a couple hundred kilojoules. So to ionize all the way is 10 times-ish that much energy. And we calculate, if we're going to do a change in energy, so calculate a spacing, calculate the photon energy that would be absorbed, then we take the final state minus the initial state, so minus z squared, the constants, and this is 1 over n squared for the final state minus initial state, and you'll get this amount of energy. And if it's an absorption, delta E will be positive. If it's an emission, delta E will be negative, and just depending on what the size of n is. Okay? And we know that's photon emission in this case. I have it dropping from a high initial value to a small final value of n. So if you look at hydrogen or 1 electron systems, you can predict all the transitions since you can calculate what we just did there, final minus initial for each one of those. You can calculate all these photon energies. And for hydrogen, the photons are in the ultraviolet region. And we saw that when we looked at our little mercury spectrum, we saw emissions in the ultraviolet. We couldn't see them with our eyes, but we could see them on the phosphorescent screen. So those are all the transitions that end in principal quantum level 1, but you could have transitions that end in principal quantum level 2. And those are in the visible. So you'd see that light. And we did that for mercury. We saw some visible transitions along with our ultraviolet transitions. And these are emissions because we excited the atom with energy. It was in very high electronic states, and photons were being emitted as the electrons relaxed in energy. So these are the famous visible lines for hydrogen. And then if the final state is n equal 3, there's another set of transitions, and these now are lower energy, and these are in the infrared. We can't see these again. So we can see these with our eyes. We need special tools to see this one and this one. And it's kind of cool, this new telescope in space, it has the infrared goggles. So it is looking, it can look at many wavelengths in particular, but it's looking for infrared. But the objects are emitting in infrared, and you can see, you take the infrared emissions and you just subtract to get them down into the visible range, and then you can draw a picture of the stuff that it's seeing. And that's why we're getting these gorgeous high-resolution images from far out in space and they're colorized, even though the telescope is just looking at the infrared. In fact, it looks at all. You can do the same thing with X-rays. You can look at the X-ray spectrum coming, but just shift, that group of frequencies from X-ray up into the visible, and you can make a visible picture of it with colors. And there's been some of those in the press as well. But that brings up a good point. You can read in a textbook and you can say, there's hydrogen gas out there in space. And you got to wonder, well, nobody went out and took a sample of that. How did they know? Well, this is how they know. They look at that cloud of space, and there's excited hydrogen atoms in that space, and they're emitting in their characteristic spectrum. So you can say, oh, something that has that pattern is hydrogen. This is hydrogen atoms. It might be hydrogen gas in space, but there's probably hydrogen. There's enough energy in some of those hydrogen clouds that you have atoms as well. But you can look into space. The light comes all the way from space to your eyes. And then you do that thing that we did. You separate the light so you can see the individual lines. And then you can identify the atom from light years, millions and millions of light years away. You can tell what that atom is in space. That is just really cool. As long as we're talking about atoms and their identity, all of the atoms, as far as we know, were made inside stars. That's where all atoms come from, as far as we know. So that means those hydrogen atoms were once inside stars. And the wackier thing that breaks your brain when you think about it too hard is every atom in your body. Every frickin' atom in your body was once inside a star. You really are stardust that somehow congealed into this. Okay, we can see it happening here. So if I could have a shot of this little device here. Here we have some gases trapped in tubes, and we can, oh, Karen didn't bring out our little metal rod. Well, I can do it. I'm pretty smart. I can probably do it right here. This is a stimulation device. Very stimulating. I can excite these atoms, these gaseous atoms, with an electric charge from this device. We can probably see it working. Do you have this? Can you give me just a slightly wider camera shot? I don't even know if this is going to work. Okay, that's good. That's good. I just want to see the interaction here. And the background isn't that good, so I'm just going to turn this up. But there, yeah, you can see that. So that's what I'm going to do to the poor little atoms. What? Oh my God, it fries. Ooh. Reset. Oh, it's going to auto reset. I hope. Okay, I'll remember not to do that. Oh no. Let's just turn that off and on again. Well, while we're letting the system recover. Karen, remind me not to electrify the counter. When we're doing this. So I'm going to do that. Well, I'm going to leave this off because I'm going to do it again, and this time it's insulated, but it still might muck with the screen. I'm going to do that same thing here. Take this charge back here, and yeah, bring the lights down quite a bit. And if you have your shot composed, I'm going to excite these. Getting some juice. You see that happening? I can't see. Oh yeah, there they are glowing. As they emit the spectra they emit from their excited states, they relax back down to ground states. And you saw in particular the neon one there that was orange. And this is from the old days. You guys probably don't even know this, but in the before times, before LEDs, you actually had colored signs, but they were filled with gas. And you would just do that. You would just zap the gas, and you could make colored signs out of tubes of glass, and they were called neon signs. And they're still kind of, sometimes people still call them that. Oh, there's the neon sign. It's not neon anymore. It's LEDs, light-emitting diodes. But it's just a historical reference to those old days. Thank goodness we came back to life. So let me ask you this: which transition in helium occurs at the same energy transition as hydrogen? Let's talk through this one together. We've already done it. So this is just to remind you. So there's a transition and a tradition. There's a transition in helium plus. Now, what is helium plus? It's a 1-electron system. Z is 2, but you've taken off 1 electron, taken off one of the negatives. Now you see the positive charge on the nucleus. So there's 2 pluses, 1 minus. You see a total He plus system. So it's a 1-electron system. It occurs in the green. Where is it the same for 4 to 2 in hydrogen? Which would be the same transition in hydrogen that happens in helium. And there it is in hydrogen, emitting green from 4 to 2. In helium, remember we already did this. We said that since there's this n squared, we have every other orbital energy overlapping. So 4 to 2 in hydrogen lines up with, oh, for goodness sakes alive, lines up with the 8 to 4 transition in helium plus. And that is just because there's that z squared on the top. Z is a factor of 2 bigger, square it, you get 4, and then the energy levels overlap like this. And we saw that for the standing waves in 1 dimension, and here we're seeing the same thing of atoms with a factor of 2. When we did it with a standing wave, we changed the box to a factor of 2 bigger. And we said, oh, we'll have the 2 and 4 levels overlap. I think we did 1 and 2 and 2 and 4. When we did the box of length L, I think we did this transition that overlapped with that transition. When we did the box where L was 1 and then a bigger box where L is 2, factor of 2 in the box did the same thing that this does for the atoms. So that's very satisfying that a quantum effect is just a wave. So if it's box L equal 1 and L equal 2, that's like the violin string. You pluck the violin string of length L, ding, 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 and you get a note, a standing wave. And if you make the box 1/2 the size, put your finger on the fret, and now the box is 1/2 a size, you should still be able to make that note. Different set of standing waves, but you should still be able to make that note on the violin string. There it is, ultraviolet. We saw, in order to ionize hydrogen, it took ultraviolet radiation, or bigger than ultraviolet radiation. Ultraviolet it could absorb. But if you keep going higher, and even the high energy ultraviolet photons ionize hydrogen. And that's true for many atoms and many molecules. Ultraviolet radiation is high enough to ionize. And you may have heard me say this already. We call it ionizing radiation. Those high energy, the X-rays and gamma rays and ultraviolet rays are ionizing. And that's why they're damaging. Because if you're going to pull electrons off an atom, you go, okay, well, you just make the positive charge. If you pull them out of molecules, it's those electrons were holding the molecule together. And if you start ionizing the molecule, you're tearing apart the bonds. And that's exactly what happens when you're exposed to ultraviolet radiation just from the sun. it's dangerous. It causes cancer because the molecules that are getting ionized are DNA in your cells. And the DNA is going, oh, I'm fine, and then breaking all the bonds, and then that DNA is like this and causes mutations and cancer. So ionizing radiation is dangerous. But here it is. This is the spectrum of the sun, and you could see if this were in color, I don't know why I have this 9 billion-year-old solar spectrum, but right down in here, those visible lines of hydrogen are apparent, not very apparent in this picture, but you can see the spectral lines coming from the sun, and you can figure out the composition of the sun. Okay, so that brings us to this, this next step. We've been saying that we can just apply z squared over n squared as long as you have one electron. And then we said, well, we're still going to kind of apply it if you have more than one electron. We're just going to say the orbitals look the same whether you have one electron or more electrons. And the extra electron we just treat as a perturbation. It's just a little different, and it's a small perturbation, so we can use the same orbitals for both hydrogen and helium plus. You can use exactly the same orbitals because it's one electron, but helium neutral, 2 electrons. We also use the same orbitals, but the energy distributions do change. So for one electron systems, we have this energy, the ionization energy. I've taken the negative sign off. I'm now calling this the ionization energy, going from n equal whatever it is to n infinity. That's an ionization energy. And that's in the ultraviolet for many atoms. You go from even the ground state out to separated far in space that ionizes the system. And we know for hydrogen, that's 1300 kilojoules for 1 mole of electrons, 1 mole of hydrogens doing that. For hydrogen plus, it's 524. You would do the same thing. You would put 2, and you're ionizing from level 1. So 1300 joules to do that, 1548 for the helium. So there's that factor of z squared, making this energy much harder to pull the electron off of helium plus. And why is that? Well, yeah, there's 2 positive charges holding the electron on. So you have to pull that off, and you get that factor of z squared when you pull that electron off. So 4 times as much energy to pull it off helium plus. But what about helium atoms? The neutral atom. Now I'll pull an electron off and see what that ionization energy is. And what I find is that ionization energy is, well, you would expect it's going to be a little different because now you have 2 electrons and 2 positive charges, and you're pulling 1 electron off. So it should be different, but how different is the case? Your first guess might be, well, maybe half as much. You know, you've got 1 positive, or you got the 2 positives, the 2 negatives. You pull 1 electron off. Maybe that 1 negative cancels out, you know, a positive, and it looks like this electron is looking back, seeing 2 pluses and 1 negative. Maybe it's just seeing 1 positive overall. But if that were the case, it would look exactly like this. If you cancel out 1 of those positives, it would look like an electron looking at 1 positive. That's this. But it isn't. It's more like this, 273. So what we get is this impression. Sure, that electron has an effect, that extra electron, but not 1 full. If it was going to shield, if that extra electron was going to shield one full positive charge, then we'd expect it would look like this. This is one plus charge and one minus charge. This is, we're talking about two positive charges and two negative charges. When I take one of them off, does the whole system look like +1? No, it doesn't look like +1 because then it would look like that. It looks like something in between +2 and +1. So the electrons do have an effect. They have a shielding effect. They block some of that charge, but not all of it. This is called, we could calculate, we could figure out what this energy is, and we could plug the energy into Z over N. And we could calculate what the effective Z is. We could calculate a new Z based on the fact that we know what the energy separation is. So do the experiment and bulk calculate that. We know Z isn't 1. We know it's not 2. It's somewhere in the middle. But we can calculate it because we can ionize that species and calculate a Z. That Z that we calculate would be the effective nuclear charge. It's not the full nuclear charge because there's another electron in there messing with it. And that electron you pull off doesn't see +2, but it's not fully shielded by the other electron, so it's not +1 either. It's somewhere in the middle. It's the effective nuclear charge. If you go to 1s, 2p1, now this is still 2 electrons, one of them in the 1s and one in the 2p. So now the electron that you're going to ionize is out here in 2, principal quantum level. There's 1 electron in the s level. Is that a different story? Does this electron, now that it's down there in the 1s, it has the 1s all to itself, the other electron is out here in the 2p, is that good shielding? Does that 1 electron cover a full or shield a full positive charge? And it turns out almost yes. So if you ionize helium with this, the excited state helium, so there's already 1 electron here, there's 1 electron down here. Oops. There's an electron here, and there's an electron here. And this electron is looking back at those +2 charge on the nucleus. This electron's looking back. This one's in the way. And it looks like he sees almost exactly +1 because his ionization energy is the same thing as a hydrogen from this state. And the hydrogen would look back at +1. Okay? So there's this fantastic shielding effect from the nucleus. The electron in the 1s shields the 2p very well. It didn't shield the one next to it in the 1s very well, but the 1s shields the 2p quite well. So the take-home lesson is S electrons shield p and d electrons very well, and you get effective nuclear charges, and this is what you see reflected here. Quite a beautiful experiment. And you kind of expect that to happen. Those electrons are in there, and they're negatively charged, and you are negatively charged. So in a sense, you're attracted to the plus that's there, but there's that negative in the way, and you're repulsed by that. It's if, let's say you were at a party, and you're there relatively early, the dance floor is open, there's one person on the dance floor who you find particularly attractive. So naturally, there's the attractive force, and you would maybe be attracted and walk right over to that person. But let's say that in between you, in between you and that person, there were something that you found particularly repulsive. Say it was at Stanford and there were a bunch of trust fund babies on on the dance floor. So you would be here and you would not be quite so attractive. In fact, you'd be more likely to leave. You'd be easier to ionize in that state. So that repulsion, that tension between them is what does it. Oh, did anybody recognize the music that was playing when we came in? I'll play it again. It was Green Day, and I know you probably recognize the name Green Day. They're a local band. They started right here in Berkeley, local kids. They wrote this song. This is from their landmark album that made them all stars. They had this song. So if I could have the audio, if I could have the audio from the lectern, and we just listen to that. Lyrics? Yes? Go, please. Play. Are we going? I'm a little confused why this won't play. Are we up there? Yes. Let's reload it. Let's reload. Okay, maybe we won't hear it. It was playing when you got in here, and I cannot make it play again. Is that because, no, it's just not even moving. The, oh, for crying out loud. Let's do this. Screw you, YouTube. We'll start you again. And we'll... Okay. I'm almost there, broken bones and nasty guts. Accidents will happen, but this time I can't get up. She comes to check on me, making sure I'm on my knees. After all, she's the one who put me in this state. If she don't tell my lady, she just stared. I better tell her that I love her. What would the lyrics be if Green Day were actually singing about ultraviolet radiation? So you know what I did. I wrote them about ultraviolet radiation interacting with atoms and molecules. So can anybody sing this one? Okay, I'll do it. Get that gum out of my mouth. I'll try. Okay. Green Day, Pulling Teeth, science version. I'm all busted up, broken bones I've come undone. Radiation will happen, and this time I've absorbed some. It's incident on me, and it's H nu equals E. Can't you see it's the one that has me in excited states? Here it is. Is it ultraviolet? Am I perturbed? I better emit some energy. In the form of a photon or two, you know it's H nu equals E. For now, all around in my ground states where I'm found, radiation can't touch me. Everybody, unless H nu equals E. All right, congratulations. You can do the karaoke yourselves. Okay, let's look at this shielding effect now in more detail. So when L equals 0, you have s orbitals, and there's s1 through 4. When L equals 1, you have the opportunity to have 3 equivalent orbitals. But now we're saying that the s electrons, all of them, the 1s and the 2s, the 1s is a very good shielder of the 2p. So we were kind of writing previously, we were writing the s and the p at the same energy. But now we're saying, no, these electrons don't see the full positive charge. They are higher, and that means higher in energy, right? Weaker attraction. It'd be easier to pull them off. If it's easier to pull them off, they're higher in energy. They're closer to ionized already. They're closer to ionized, which is 0 energy, top of the board, closer to ionized because they see less positive charge if there are some 1s electrons here. And that is true for the 3p as well. And when you go to L equal 2, now you have d orbitals, and those continue to be very well shielded by the electrons below them. So well shielded that this they go much higher in energy than the principal quantum level 3. They even start to reach above principal quantum level 4 because of these kind of effects. So the overall ordering is not exactly, if you talk about energy, is not exactly n equal 1, n equal 2, n equal 3. You have, if you get high enough in n equal 3 and you have a very shielded system, then the d orbitals can have lower, or excuse me, the d orbitals can have higher energy than the 4s orbitals. So what it means is the order of filling is not 1s, 2s, 2p, 3s, 3p. It doesn't go 3d, but the 4s are accessible. They're actually low. So it would go maybe 4s electron before the 3d electron. So it would be slightly lower energy, that configuration. Now, this is a bit of a hand-wavy explanation, and all those electrons have to be there. So if you just have one electron, then the 3p and the 3d are the same level. But if you start putting electrons down here, these are very well shielded and they're easier to ionize, going up in energy, easier to ionize. Because they're higher energy, closer to 0. And that's from the shielding of all these electrons down below it. S-H-I-E. Ding. See why I don't write on the board very often. I before E, except after C, or sounding like A as in neighbor and way. Just chant that to yourself. So what we find then is that little bit of energy raises, it's that far above 4s for in some situations, depending on how many total orbitals, how many electrons are there, etc. We won't get into the details. For you, all it matters is the ground state electron configurations. The ground state electron configurations, 4s orbitals fill first before 3d, and even that's a little hand wavy because it matters the total electron system, not just the next electron you put in. But here I'm just drawing the picture. So here's 1s, 2s, that's got a node. So it's higher energy than the 1s. There's one node in the 2p as well. One node in all of those. 3s, there's a node here and a node here. So we have two nodes. Here are two nodes, a radial node and a angular node in the 3p, and the s below it shielding the p. And then here's a d with its two angular nodes being shielded by all of these s electrons below it. And here's the 4s with its three nodes in the radial nodes in the 4s state. But this summarizes it. You go 1s, 2s, 2p, then 3s, then 3p, and then 4s electrons appear before 3d, and you see that in the periodic table. So you see on the side of the periodic table, it's going down is principal quantum level, 1, next row 2, next row 3, next row 4, so it's calcium and potassium, 19 and 20, and then scandium there, it has the electronic configuration 4s2 3d1. So it has these electrons filled first and paired before you got the d electron. So that's basically the story. We're not going to delve in it too deeply. The periodic table reflects that. It says 4s2, that first group of d orbitals is there. And we'll talk about it. We'll bring the periodic table down here and talk about it in more detail later. We'll also just, this makes it on the exam all the time. Which atom or ion has the lowest ionization energy? Look at hydrogen excited state. One electron, neutral, the electron's in the 2p. Helium, also one electron, helium plus. The electron in an excited state, out in the 3p. And then lithium, also one electron. 3 total pluses, one electron, makes the total charge on the ion +2, but the electron's way out in the 4p orbital. Okay? So which one of those has the lowest ionization energy? Lowest means what? Closest to ionization, highest. It has the lowest ionization energy if it's the highest energy orbital. It's closest to 0. Talk about that quickly among yourselves, and we'll take a vote. What do you guys think?
4p, so it's the highest edge.
It's kind of, you know, this one's kind of silly. Right? It's obvious, right? They're all one electron. But wait a minute. The 4p is the highest, but it has 3 pluses. So you gotta be a little careful. There's 3 pluses hitting that 4s. There's only 1 plus hitting that 2p. So it is z squared. So there is that factor. Does that cancel out the fact that it's at 4? So z is 3, but n is 4. Does that get you higher than here? Z is 1 and n is 2. So it's 1/4 versus 9/16. Ooh, it's close. 4/16 would be a quarter. That's 9/16. And you have to, and if you remember, it's minus 9/16. It's minus 9/16. So that's a little over a half. 8/16 is a half, and a quarter is, that's halfway down. A quarter, it's higher. Okay. Good discussions there. Let's go up and see what you're thinking. You can go ahead and register your thoughts if you'd like. Oh my goodness, hydrogen 2p is super popular. Wow, nice job. So what you're doing is I have to ionize these. In general, if it's farther away from the nucleus, 4p, that should be, everything else being equal, 4p is easier to ionize, right? In fact, if it were hydrogen in the 2p or hydrogen in the 4p, then 4p, of course, easier to ionize. It's up in principal quantum level 4. But this guy in the 4p has 3 positive charges holding on to it, where this guy in the 2, this electron in the 2p has just 1 positive charge holding on to it. So we should look relatively carefully at the ionization energy here is a quarter R, z squared over n squared, 1 squared over 2 squared. The ionization energy for the helium in the 3p is 2 squared over 3 squared. And the ionization for the lithium is 3 squared. And don't make that mistake. +2 does not mean you put 2 in there. +2, it's a 1 electron system. +2 means there's 3 positive charges and 1 negative charge, 9/16. So, and remember, if we plotted them out, we've put the positive sign in here, but if we plotted them out by energy, they would all have, so if it were just energy, then there'd be the minus sign there, and that's what tells you you would have minus a quarter R, and then this 4/9, those are both right around a half, 4/9 and 9/16, they're all negative, so these energy levels are down lower energy than this one. This is the easiest to ionize, okay? The easiest to ionize. All right, fantastic. We'll see you guys tomorrow.